to refer to something that Christian was saying yesterday, and referring to the paper that he wrote with Nick about emergent space-time and empirical experience. And I remember one of his slides, and in which he was saying something very interesting. Avoiding the charge of empirical incoherence requires that a theory must be shown to admit emergent space-time. And also this has an important role in the context of justification. And this is quite important because, I mean, having a theory which is so much in advance with respect to experimental, testable situation, I mean, it's important to formulate a notion of justification which does not rely just on the idea of empirical, of testing, empirical evidence. Anyway, what I'm trying to do here is to formulate the way in which to share with you how the notion of emergence looks in my eye of space-time string theory, how I would define the notion of emergence. And in the draft of my paper, which is in Dropbox, and it's a work in progress, so I basically emphasize that I call this emergence of ordinary space-time string theory because I want to emphasize that this is the emergence of the four-dimensional general relativity space-time. I'm not talking about emergence of higher dimensional space-time required by string theory, so extra dimensions, and we saw these beautiful talks yesterday about duality. The way in which they talk about emergence in that context has a completely different methodology, which is not the methodology I'm using here. Let's start with that. So my way of thinking, my notion of emergence, of ordinary space-time emergence, basically it has two ingredients, like recipe, okay? The first ingredient is something that I want to unravel here. I spoke about that, I remember, in the Summer Institute of Philosophy and Cosmology. Basically, it amounts to formulate the idea that string theory predicts the existence of graviton. Predicts the existence of a spin-2, massless particle that can be identified with a quantum gravitational force. Also in the paper there is a longer draft on this part. What I can say, I know that this is going to be, what I'm going to say in the next 2 minutes is probably very boring for physicists, but I thought for people who are not physicists, what does it mean to say that string theory predicts gravitons? Well, it just means that this particle appears in the spectrum of state of the quantum string, and how a particle appears in the spectrum of state of quantum strings basically amounts to say, well, it appears in its mathematical clause. It's a vector, it's a state, it shows to have some mathematical property that makes everyone thinking that those mathematical property of that mathematical entity seems to describe very well the physical particle postulated in the case of graviton. But okay, so I'm not going to talk about this first ingredient, but let's keep it in the back of our mind. And this presentation is about the second ingredient of my recipe for emergence of space-time string theory. And basically amount to something that Nick very, very nicely mentioned yesterday in his presentation. So the derivation of general relativity out of string theory. And basically, let's say more precisely, so the derivation of the cosmological Ricci-Flass solution of the Einstein equation from a formal property of the theory. We spoke about conformal invariance. So basically, you can see, right, these two ingredients. This is just a very, very brief anticipation to give you an idea of what we are going. I mean, where are we going? So on one side, it predicts gravitons, the theory. On the other side, it's telling it's also telling us that the coherent superposition of infinitely many particles shows a collective behavior which is governed by Einstein field equation. These two things together, which we are going to see in a bit more detail, are, in my eyes, the notion of emergence, ordinary space-time emergence in string theory. Okay? So, I want to mention something very important, and I'm going to use the black pen for that. Nick yesterday anticipated a crucial point. So basically, he started with the bosonics, the string action, in which there was just a gravitational background field, right? And then we will see how to get Ricci flatness condition from that. But of course, this is a toy theory. The bosonic string theory is a toy theory. It is a theory without matter. And so the issue was, well, but if I start to work with a more realistic model of action in which I can put there some matter field, am I still able to get out general relativity? And Nick showed, quoting from a couple of guys, I don't remember the name, but there was the quotation yesterday in your slide, so you can refer back.
So, yeah. 3 demos.
Okay. Yeah, unfortunately, I forgot to. I mean, I read the paper, but I don't remember this. Okay, that's one word. Sorry. So he basically wrote down this equation. I'm just reminding, okay? So basically, if you have if you let your string interacting with the gravitational field plus a matter field, you will have that as the first order of alpha 1, the stress energy tensor of the Young-Mills field will appear. So conformal invariance, even if you introduce, of course, this is a heterotic string theory. It's a theory. We don't have just conformal symmetry. We also have supersymmetries. One thing that it didn't come up yesterday is this. Yeah, we are taking an expansion of the classical action using the order of half prime, which is the unit, the string length scale, because we are working with. We will see in a moment. We are working with. We are starting with a classical action with a curve metric, which is weakly curved. Okay. So if you want to do an expansion, a perturbative expansion in a highly curved space-time, we will need another kind of expansion, which is basically based on the powers of the genus of the worldsheet. Okay, because of course higher curvature means higher energy. It means that the worldsheet of the string will have more holes, right? I mean, I don't know if I'm saying something completely new, but the genus of a Riemann surface is the number of holes that this Riemann surface has. The more are the holes, and the more there the strings are doing things very complicated, like splitting, unifying, and it's a highly complicating interactive model. Okay, and that's to connect to Nick that yesterday prepared very nicely the ground for what I'm going to talk. Okay, so let's say that. Let's talk about this second ingredient, which is a very nice mathematical derivation, which combines together two different perspectives. So on one side, we can derive some facts about strings in a low energy regime of perturbation, and then on the other hand, at a certain point, we will apply to this fact, we will derive something else, applying something that I like to call a guiding principle. This guiding principle is something that obeys to, I would say, part consistency reasons, but also historical reasons. And this is going to have some kind of conceptual role in the definition of emergence that I'm trying to develop. So we will see both, okay? So, okay, let's start with presenting this mathematical derivation. No, wait, yes, okay, yeah. It's okay. So let's say that just few things. What I find beautiful about this mathematical derivation, as a mathematician and as a philosopher, is this, that it shows how quantum string theory imposes an ambiguous constraint on which kind of background gravitational field the string has to interact classically. Okay, beautiful is a matter of taste, of course. I say it is impressive, and what I also find impressive is that this requirement, this constraint that the quantum theory is imposing on a larger scale theory, come from a formal feature of the theory. Okay, so far so good. Okay, so yesterday we mentioned conformal transformation, and I thought maybe, since you didn't show how, well, I don't know, I probably apologize with the physicists who already know that, but okay, this is how, no, this is the Weyl invariant, this is a Weyl transformation, okay. Few words. I know everyone knows what a conformal transformation is. Basically, I'm talking of, my manifold is the word sheet of the string, which is a surface, a Riemann surface, and a conformal transformation is a diffeomorphic change of coordinates over the manifold, along with a Weyl transformation. Which doesn't mean that the Weyl transformation or conformal transformation are one the subset of the other, okay? Because conformal transformation acts on coordinates, the Weyl transformations act on the metric tensor, they stretch or contract the metric tensor. So think to conformal transformation in this way. I don't know if that is useful. It is useful if I say that, or how? No, it's not.
Should say it, never know.
Okay, so think to isometries, right? Isometries are rigid rotation, so that is a transformation of coordinates. You take a point.
I would say Weyl and conformal.
I'm sorry?
One's a Weyl transformation, the other is conformal.
No. Some people tend to identify, maybe you identify conformal transformation with Weyl transformation. Is that what you're saying?
I would.
You wouldn't.
No.
Okay. No, I tend to think like conformal transformation. Like, let's say, think to an isometry, but I don't need to explain to you that because you know much better than me. And so you know that is a transformation of coordinates. It takes a point x, it brings the point in another point y, but the tensor metric over x remain the same if it is a rigid rotation, okay, on x and y. If you have a conformal transformation, you have that you take a point x, you bring the point x on point y of the same wordsheet, but there you don't require that the metric tensor over those 2 points has to be the same, but it has to be the same up to a Weyl factor of rescaling. So it's basically a bigger. That's why when the definition of conformal transformation is given in this sense. So using Weyl transformation and diffeomorphic change of coordinates over the wordsheet. Is my pronunciation understandable? Yes. Okay. So being conformal invariant means be Weyl invariant along with diffeomorphism invariant. Okay, now this is a Weyl transformation appears, and usually the conformal factor here, the scale factor, is the omega omega depend on sigma, so on the coordinate over the worldsheet, but usually the way in which it has been used a lot in string theory is taking sigma omega constant, and so e to the power of d minus 2 times omega is the conformal factor. Okay, so this is a Weyl invariance. I'm giving to you the definition of Weyl invariance because when we say that the conformal invariance is broken, what it is really broken in the quantum string theory is the Weyl invariance. Okay, and therefore it is not conformally symmetric. I want you to have the definition of infinitesimal, but we can come back on that. Infinitesimal Weyl transformation, because this is going to be useful to sketch the basic passages of this formal derivation. And I want to tell you, I'm not bringing any revolutionary result about string theory. I'm referring to the wonderful work that has been done by Polchinski in Introduction to String Theory Volume 1 and Maurizio Gasperini, particularly Maurizio Gasperini, Elements of String Cosmology. So I just try to take what they say and to put in human words and more easy going, and so probably more approximative. Okay, so action, Nick was writing down, I think without 4 pi, I'm sorry. Yeah, okay. So notice that this is the classical action of a string. We have an integral over the worldsheet, which is a surface. Sigma is sigma 0, sigma 1. So sigma is a 2-dimensional parameter. Gamma, you call that H. I call this gamma. It is the intrinsic metric of the string worldsheet. And then we have these fields, x mu, x and g u nu, which is referring to the target spacetime. Whenever you read mu and u, we are thinking about the target spacetime. Whenever you read A and B, we are thinking to the metric over the worldsheet. Okay? So, something important about that. Yesterday we said that, Nick said that. The crucial fact is that the classical theory is conformal invariant independently whatever is the semi-Riemannian matrix that you put there. So there are no constraints of G mu nu, okay? It doesn't have to, if you are just studying the classical theory, okay? You're taking your first course in string theory, and you know that this is any Riemannian metric, and conformal invariance doesn't impose any constraint. Okay, so at this point we want to quantize. So a way in which I quantize this action is the well-known the quantum loop correction around the classical solution. So x mu is my classical solution. So you basically start to perturbate with quantum fields. Of course, as everyone knows, these quantum fields are not solution of the classical action. And so what you are doing, perturbating this classical solution, is basically moving from a classical action to an interactive quantum field theory. Of course, this perturbation of the classical solution will bring about the perturbation of the derivative of the fields over the worldsheet and the derivative of the G mu nu, the tensor metric here. Okay, these two expressions, okay, they didn't show up like this. I mean, you can derive them after complicated change of transformation, but finally you find a reference system which is called Riemannian normal coordinates, and you can find the description of this reference system in Gasperini, chapter 3. I don't remember the page. Well, it's in my paper. It's in my paper, but it's there, chapter 3, Elements of String Cosmology. So you have the merit of this change of this reference system is everything is very clean, very nice. It's not a mess. It's not too difficult to follow. Here you see down R mu nu alpha beta. That is the Riemann tensor, the Riemann curvature, and it's a 4-index tensor, and this is very important because we will get Ricci tensor from this guy. Okay. Now what we have here, we quantize the theory, so we have a new action which is S bar, and which is the classical part, the unperturbed part, plus a quadratic part, because you see here I just stopped to this order, to the order zeta alpha, zeta beta. I didn't go. Okay, how does it look, this quadratic part? If you do some math, it is not difficult. You just replace the expressions in your classical action, and you do some math, and you get this expression for the quadratic part of the action. Can you read that? Because I cannot. Okay, no, I'm glad to see that this is better. Okay, so, okay, I'm going now to have to compactify a bit my exposition, okay? But this part of the action contains a divergence, right? This will be immediately clear for those who knows quantum field theory. Well, why is that? Well, you can say that. Think to this expression. I prefer to think to this expression not in the momentum space, but in the position space. And so you can say that you can see that the propagator for the scalar field diverges here. Are everybody with me? Would you want me? I don't think the physicists here, maybe it's even insulting for some of them if I write down the propagator expression. I don't know. It goes like the logarithm for. Do you want me to write that down on the blackboard?
I think in the interests of time, probably we'll just take your word for it that it diverges.
Okay. I swear it diverges because sure, because it depends on the logarithm that goes to 0. The argument of the logarithm that goes to 0, so you have a divergence. Okay, so now you have to do something. You don't want to have an action with divergency, and so basically what you do usually quantum field theory is to kill the infinite with another infinite, and so you have your newest action, quadratic action, is the renormalized one plus the control term, and this is the control term. You see here? Can you see here? That's interesting, right? So look just this. This is the important part. Because this control term which kills the infinite, this limit, this is sigma, okay? This is the parameter over the worldsheet. This limit is introducing a dependence on the length scale, okay? And it's like, well, when you normalize a theory, you say, well, below, I establish a certain threshold, and below that threshold, I don't care what is going on, even if there are divergency, I'm just not going to look below that threshold. But here is the problem, because I started with a conformal invariant theory, so no dependence on any length scale, but now I have a part of that action, quantized, which depends on the length scale. So, what should we do at this point? There is a way to fix this problem, and part of the way to fix this problem consists in showing why this is not conformal invariant. Because if you see with your eyes why this is not conformal invariant, you will understand how the Ricci flatness condition comes out. Okay, so. And now I'm back to Gasperini, because Polchinski uses, Nick was sticking to Polchinski a bit more. He was using the correlation functions, which is pretty much the same, okay? I'm just working on the worldsheet here. What you were doing with the correlation function yesterday was to study what's going on in the target spacetime. We were doing it in two different, it's the base, it's just two different languages. Maybe it is interesting, right, to see in two different perspectives. Okay, so now what I want to do, okay, let's compute this integral, but in order to compute this integral in a finite form, I have to change the dimension. Remember, our dimension now is 2, because the worldish is 2-dimensional. So I will apply a small deformation of the dimension, just a dimension a bit more big, more big than 2. So 2 plus epsilon, just a tiny more. And so there is a way to mathematically, which I'm not going to do this now. It wouldn't. Those blackbirds are too small. That limit becomes this limit. Trust me. Okay? And so you rewrite the contour term, which is now in 2 plus epsilon dimension, like this. And now things are becoming very nice. Look here, this is very nice. You can see now, for those who are experts, that the Ricci tensor comes out from here, the contraction. And it's not just that. Okay, I say here, yeah, I'm sorry, I don't know why it's so messed up here. So this is how you get the Ricci tensor, and now you can rewrite in the with the Ricci tensor the action in dimension 2 plus epsilon. But now, okay, we still rewriting in a dimension bigger than 2 this contour term. Okay, now let's see why it is not conformal invariant. Well, it is not conformal invariant because, of course, when I say it is not conformal invariant, I have to show that it is not conformal invariant in dimension 2. Okay, now I am in dimension 2 plus epsilon. It is not conformal invariant because let's take an infinitesimal Weyl transformation, right? The one I showed you before. Maybe you wonder why I was showing to you. This is how it was, the infinitesimal. So you just take the definition of infinitesimal transformation that I gave. The definition of Weyl transformation I gave you here. You take the derivative with respect to omega, and then applying to this case, you get that your becomes this one. This is the derivative with respect to omega. Remember that omega is the scale factor. Okay. Look here. That's crucial. This derivation will produce an epsilon out in front of the integral. And this is going to cancel with the epsilon here. Look, I can do whatever I want with this limit. For those who are wondering why this limit is going out of the integral like that, well, it is basic things, right? You learn this in school. So you know that if, I'm bringing out a variable which has nothing to do with the variable of integration. So I can do whatever I want with the limit. I can switch if there is no overlap of variables. And so epsilon and epsilon, they cancel out, but okay, so what I get is something like that. Okay, that's interesting. I'm still in 2 plus epsilon, but now, you see here, right? Epsilon disappeared. So now I'm back, I take epsilon going to 0, and I'm back in dimension 2, and now I have the variation of the contour term expressed in this way, and there is no way to send this quantity to 0. I want the variation, the infinitesimal conformal transformation of this contour term going to 0, unless this is equal to 0. This was really a short, compact exposition of how you get the Ricci flat condition here. So, yeah, questions? No? No, these are clarification questions. But I mean, okay, you can ask whatever you want, really. I mean, not just you, everyone. I mean, because I feel like before presenting, I am very concerned to cover everything, and so I say, okay, questions at the end. But then I want you really to follow what I'm doing. So I will take some extra time. We can skip lunch. And I answer all the questions.
There is no lunch to skip.
Well, the flights are all tonight, right? So we can stay here. So, I mean, if you really, I'm sure that all of you follow very nicely. This is not difficult, right? It's okay. So we have this vacuum solution. We said we just took a toy model of bosonic string action. So now, keep in mind this. So What we have here is that that quantum string theory is telling that, as I said before, the string can interact classically only with the gravitational Einstein gravitational field. But what it is interesting, if you combine this result with what we just said before, when I said the gravitons are basically closed strings modes of oscillation, right? So you see that this result with the other consideration, with the first ingredient I gave you, really open a window on a much finer perspective. So when you have a string interacting classically with the background, gravitational background in this case, what it is really going on there, the quantum dynamics underlying this effective representation is that the string is interacting with its own mode of oscillation. And this is how I tend to define the emergence of ordinary spacetime in string theory. Now, one point. Okay, so we saw so far these two things. We were in a low energy regime. Well, actually, okay, let me say this. I started from the, when I say low energy, let's say low energy regime of perturbation. But of course, when I say quantum string theory, I'm thinking to the full expansion, okay? So I'm just taking consideration one truncation, the first order, the lowest energy truncation one, okay? But you can think to that truncation of the lowest energy like a low energy limit of the full expansion, of the full complete quantum string theory. Okay, but you see, we had some perturbative regime fact, and then we applied a principle. We said we want this theory to be conformal invariant. The classical theory is conformal invariant. The quantum theory has to keep this conformal symmetry. And this is really crucial to derive the cosmological Ricci-Flapp solution, okay? Now, the point is, someone could ask, but why string theory has to be conformal invariant in the first place? Because, I mean, we are talking about deriving a theory from another, and we will move to more conceptual analysis in a few minutes. Do I have time? How much time I check?
5 minutes.
Really? Let's do, okay.
If you want to have
5 minutes?
some time for questions.
Okay. So I'll be very, very, very fast. Yes. Okay, so why it has to be conformal invariant? Okay, the point is this. I said consistency reason, historical reason. Consistency reason are connected to the fact that the only available recipe we have to compute scattering string amplitude is basically based on the fact that the string partition function is the integral of the partition function is defined over the moduli space of the Riemann surface. Okay. Okay. It has to be well defined. What does it mean? It has to be well defined. When you have the moduli space of Riemann surface, you know that each point of the moduli space parameterizes a conformal class of Riemann surfaces. This is the nature of moduli space, right? So when I take the integral of the partition function over the moduli space, I cannot allow to this partition function to depend on the particular choice of the representant inside the conformal class. I want the value of that function to be the same on the whole class, okay, which is the point of the moduli space, and that is where I am integrating. So on one side there is a problem of the conformal invariance is needed because we need to have functions which are mathematically well defined, but this doesn't mean, and I'm not able to give a more compelling reason about why string theory has to be necessarily formulated with the language of Riemann surfaces. it doesn't rule out that we could have a string theory using a mathematical language which is not that one, okay? Another reason are historical, because when everything started, I mean, the Veneziano amplitude of the 4-point scattering strings have been generalized to the n-point scattering, and the way in which they have been generalized was done by using vertex operator, and the way in which vertex operator behaved under conformal transformation, so the conformal invariant so on, it was imposed by the fact that it was imposed by some feature of the calculation concerning scattering. It was a practical reason. So, okay, this is why string theory has to be conformal invariant. I am not able to think to more compelling reasons than that. I wish I could have a more compelling reason than that in order to say this is really an intrinsic formal feature, but I think they are strong enough to speak about some kind of intrinsic conformal feature. And now, why is this emergence? Because now I will need just some more few minutes. So, as you have understood by now, when I speak about ordinary spacetime emergence in theory, I'm basically talking about an intertheoretical relation between general relativity and string theory, and this intertheoretical relation is characterized by this idea of approximation. There is a low energy limit which is included, right, in this derivation. Now, I'm not going to make a survive of the infinite landscape of philosophical debate on the notion of emergence, but I found two authors really, really very important to me, because I started to study emergence just in a mathematical way, and then I found out that I was doing something conceptually which was very close to what two people are doing. One is Batterman, and the devil in the details. Is that the title? Okay. And another is Jeremy Butterfield, who is here. If I say something wrong, you can correct me. He wrote a wonderful paper on less is different, emergence and reduction to reconcile. There is also another reference which I won't have time to go, but it's Gordon Kane, supersymmetry. I don't know if I will be able to cover this, but okay. What I found interesting of Jeremy and about Batterman is that they are using this notion of intertheoretical, so emergent as intertheoretical relation, and then that they are using the notion of, let's say, low energy limit, or limit of some physical parameter of the theory that could use another theory. And what it is different between them is that they identify emergence in two different aspects of this limit. So Batterman says that you can talk about emergence only when the limit between one theory and another is singular, so there are some discontinuity between the two theories that justify the fact that the theory which is emergent is introducing an amount of novelty, because the notion of emergence evokes the notion of novelty. And so for Batterman, emergence is a failure of reduction, but Jeremy doesn't agree with him, and he thinks that it is possible to reconcile the two things. And so we are talking about a reducing theory, in my case it would be quantum string theory, and a reduced theory, and the reduction basically is interpreted in terms of deduction, okay, in this, based on the Nagel model of deduction. So you have basically the reduced theory, the physical law, the formal property, the theoretical proposition, observational proposition, and so on, of the reduced theory are deduced by those of the reducing theory. And an interesting thing that Jeremy says that I found very interesting is that, well, at least this is my way of paraphrasing, okay, how this notion of reduction can deal with the notion of novelty, right? Because deduction seems to not to be incompatible with the notion of novelty. Well, in this deduction of physical law, let's say lower level to higher level, it is involved the change of physical scale. And so this change of physical scale, because there are physical parameters of theory which just goes towards some crucial value, this physical change of scale will produce a description of the world, which is that of the reduced theory, which is incommensurably different from that provided by the reducing theory. This is how I see it. I mean, how I tend to think in which way I could still have some space for a notion of novelty, but I want to be careful because here the novelty is a novelty in an epistemic sense. So it's just that the language of quantum string theory, because I'm applying what I say to my case, it doesn't make mathematical language, the theoretical proposition of the reducing theory doesn't make any sense if formulated in the domain of application of the reduced theory. And so there are really robust, as Jeremy say, novel behavior, regularities at the higher level, let's say larger scale, that can be explained, of course, but, from the reducing theory, but it cannot be captured in the theoretical language of the theory. Now, here is my point. I think I'm sorry, I put up a lot of stuff. I wish I could have said more. So, my point is, there is Butterman in his book. At a certain point he says, well, a way of talking about singular limit is thinking that when you have a theory approximating another theory, between the two regimes, you have a kind of no man land, which doesn't belong to one theory and neither to one theory, neither to the reducing theory nor to the reduced one. And so we need a third theory, okay, which describes this no man land, okay. One of the ways in which he characterized discontinuity. So let's look carefully to what we have been doing here, because I am inclined to think that this is a case of emergence and reduction combined together, but it depends. I think it depends on how you consider this idea that the conformal invariance of string theory is not some necessary, intrinsically, is due, there are no enough compelling reasons to think that string theory has to be a conformal invariant theory, and there is a kind of guiding principle which is inspired also by historical reasons. And this guiding principle doesn't belong to string theory, doesn't belong to general relativity. I'm not deriving a genuinely physical law of general relativity from a I'm not deriving general relativity from a genuinely physical law of string theory. And so that already makes the canonical model of Nagel, canonical model of reduction according to Nagel, maybe not easy applicable. I'm deducing something from a formal structure, but I told this formal structure has to be there for reasons which are not enough compelling. So sometimes I've been thinking maybe this is really a kind of no man's land in which there is a guiding principle inspired by reasons which do not belong to both theory. And so maybe it could be also formulated in emergence in those terms. So what I'm trying to say that still this is a work in progress. These two ways of thinking about emergence at this stage of my study seems to be in competition, still in competition, and I don't know. I will figure out someday. So time ran out?
Okay. So it's a friendly comment first. I think this is definitely a good case in which novelty of emergence is very obvious.
Say again, yeah, this is...
The novelty very obvious in this case because you start from a two-dimensional theory on the world sheet and you apply the five invariance to it, and from this calculation you end up with Einstein equations, the region. So it's kind of out of place, unexpected, right? You start with conformal theory and you get gravitation.
Of course, it's completely magic.
Good.
Because it's really something that you don't expect, because you end up with the largest scale theory.
Right.
I mean,
so from a smaller theory, which is kind of restricted,
length scale, lowest length scale, yeah.
Good. But the question I have here is when you start to talk about this Butterman type of emergence, where you always have a parameter number that goes to infinity, and from there you get emergence. What is the equivalent of the n, like a phase transition case Butterman and Butterfield talked about? Do you see an equivalent of an n that takes you from a theory which used to be finite and move you to an infinite, and from there you see the emergence novel property? Because I can't see it here.
You cannot see the analogy between what I have been doing and how...
I don't see the role of the n going to infinity in the deduction of the Polyakov action. Personally I don't, but probably I...
I'm sorry, you don't see what?
I don't see the role of an n number on the parameter that you take to infinity, like in case of Butterman type of emergence.
Look, okay.
In this, if I probably...
I'm not taking an infinity anything here. I'm thinking to the full expansion of quantum string theory. Quantum string theory is in a perturbative formulation. I'm thinking to the full expansion, okay? Right. And now I'm taking the low energy limit that end up in get rid of the higher order, and so being in the lowest regime. Is that okay? It's
a mathematical operation that you eliminate sometimes.
Yeah, it's a mathematical operation. And then I am in the lowest energy regime. So you think this is not what Butterman is doing?
I think it's a different type of emergence than that kind of case.
I'm not. In fact, I'm not. But that is not emergence. Well, no. Wait. No.
Okay.
I'm sorry. Have I been so confusing? No. The emergence is not at that stage. When I am working in the low energy regime, okay, and I'm taking the low energy limit of the full expansion, I'm not making any deduction from the reducing theory. I'm still in the reducing theory, I'm still in quantum string theory. It's just that I'm focusing my attention on the lowest level of perturbation, okay? There's no emergence there. Then, in that level, as soon as I took the limit, okay, for the energy going toward the crucial value, in this case 0, but it doesn't matter if infinite 0. I mean, Butterman speaks about a crucial value. I mean, you can also think that the energy that goes to 0 is the length scale that goes to infinite. So they are two equivalent mathematical formulations. But the deduction of the general relativity comes after the limit. It's not in the limit. And this is much closer to what Jeremy says when he speaks about, when he tried to deal with this idea that deduction is not, from a canonical point of view, in the traditional philosophical debate, is not compatible with the notion with novelty, because deduction usually, you don't have the content, information, right? We teach that to the students in logic in 102. So, and quoting from he says something very interesting. So you first take the limit, and then after you take the limit, you apply deduction. And this is something which I was doing here. And I'm sorry, I've not been very clear. Okay. Then my problem was, okay, I took the limit. Now I'm performing this deduction. Okay. Am I doing really deduction in the sense that Butterfield says, in the sense that Nagel says? Because I'm not really deriving this Ricci-Flop condition from a generally physical law of string theory, but from a conformal property of string theory. So, but this is another question. And then I said, okay, It depends on how much intrinsic you consider this formal property. If you really think that for you the reasons I gave you are enough strong, then yeah, this is my approach, this way of talking about emergence is close to what Jeremy is doing. But I also wanted to consider another perspective. Someone that could say, hey, wait a minute, I don't think that the reasons that you gave for string theory being conformal invariant are enough strong to talk about an intrinsic formal feature of the theory. And so, you know what, I think that here there is some kind of principle which doesn't belong to string theory. A kind of third field in which you are applying a principle. And that seems to evoke that maybe the notion of emergent then could be formulated in the Batterman language. If I am not misreading Batterman? Yes, I was saying Batman, sorry. Batterman language. I'm also videotaped. So I don't know, Jeremy, you can correct me if I'm misreading your position?
I think Brian has a question. Maybe this could be the last one for this session.
Thank you. Maybe I should learn this from the string theory textbook, but I'm trying and failing to understand from this expression how it is that contracting a rank 2 matrix with a 10-dimensional Ricci tensor or whatever can lead to a vanishing 10-dimensional Ricci tensor rather than, say, a little vanishing 2x2 corner or projection onto the world sheet or some such. Does the...
you mean how it works that contraction?
Well, yeah, why shouldn't I get that Ricci tensor times the gradient of your big X's? Which will be like, 2x10 and 10x2 matrices. So I feel like I ought to get only a a non-trivial 2x2 condition instead of a non-trivial 10x10. So is gamma somehow arbitrary or being integrated over? Because you're integrated just over the world sheet, not over the metrics.
Yeah, I'm thinking over the world sheet.
Yeah, I guess I don't see how that works.
You don't see how that is that contraction out there because I'm integrating over the world sheet?
No,
Okay,
no. If you're integrating over the world sheet, that makes my problem real. Because if gamma...
But this has nothing to do... I mean, look, mu, look there, alpha, beta. There is no A, B there, okay? So this is just a...
That's 10x10, but you're contracting with something which is like just which is 0 everywhere except in one little corner, at least if you choose your coordinates in the right way, right?
Sorry.
I mean, the rank of that, derivative of big X mu with respect to A, I mean, that's going to be like a 2x10 rectangular matrix. So
okay, let's say
or
that.
10x2 or whatever.
I'm pretty sure that this contraction is correct, but I don't have the notes with me.
It's a 10x10 matrix.
It's
X mu by X mu. Actually, 26
maybe I'm not
by 26.
understanding what.
Well, whatever. But the point, gamma is it runs over 2. I mean, your Latin indices.
Over what?
Your Latin indices run from like 1 to 2 or something, right? Or 0 to 1. And the Greek ones run for up to 10 or 26 or some much larger number, right?
Yeah.
So why should you get r mu nu equals 0 instead of r mu nu times the gradient of x?
No, but I'm getting r mu nu equal to 0. Oh, but I'm getting r mu nu equal to 0 not because of that contraction. R mu nu equal to 0 comes from another order of consideration.
I thought you were explaining to us that it was coming from that expression there.
Absolutely not.
I'm totally
sorry.
misunderstood.
No. Okay. Okay.
The next equation.
This is just a standard way in which textbooks.
So I don't think he's talking about that contraction.
I'm talking about the next page.
Oh. Sorry. It's not working.
I thought I was supposed to be able to see, well, this counter term.
I cannot change the page here.
This thing is supposed to be 0, and to get it to be 0, we have to have that 10-dimensional Ricci tensor be 0. I can see how a little 2x2 corner of it would be 0, but not how the whole 10x10 thing would be 0.
It has to be equal to 0 if you want to send to 0 the variation of the counterterm.
Right, that's what I don't get.
Well, do you have another way to send to 0 the deltas, which I cannot, for some reason it's stuck here, this computer?
Yes, if I could run parentheses around the gradient of x, r mu nu, I would want that thing to be 0.
Thank you so much.
Which is a much bigger
Okay,
condition.
let's go.
So
Yeah,
obviously,
thank
there's
you.
something I don't
I
understand.
think the
Okay,
idea
let
is
me
the
say, let
XNU,
me say.
XNU, you can get this patch covering any part of the space-time, because you have an XMU, XNU can take on any values, the XMUs.
So do we
That's
integrate over
what
the
I was
X's or something? Or?
But we want this to be the case. I think we want this to be the case. However, the string, whatever the string is doing. Yeah, we are going to integrate. I mean, we're going to, in a path integral, we're going to integrate over all paths of the string through target space.
Yeah, so maybe that arbitrariness is what I don't see, and maybe that answers the question.
I think you're saying because it's a sort of sum. I mean, it's a sum we're trying to set to 0, and there's many ways to set the sum to 0.
Yeah,
But
it's true. There are many ways
The
to
del
set
x
it.
is
Yes.
arbitrary, so that should
Yeah, but
Maybe that's
make it 0 in every case.
But you want that quantity to vary identically to 0, because you don't want that the counterterm as infinite breaks the product variance. And the only way to put identically to 0 is to take the Ricci tensor identically to 0.
Maybe there's this arbitrariness
Yeah.
that I'm not
So
seeing.
if I gave you some, you're saying if I gave you some specific del x's, that wouldn't, right? I could then set our union
I said it.
to something else and still get it to be 0.
Yeah,
But the del x's can be
without any
anything
union.
whatsoever.
Oh, okay.
Maybe that's the answer.
Thank you.
Did you reply to your question?
Well, I
I
think-
didn't reply to
I think we should probably close it off for now. So little time, so much to know.
Yeah.